And I'll share my screen again. We only have 5 pages remaining, so this should not take the full remainder of the hour. But this particular problem example is we're given a cross section that looks like a plus sign, and it's subjected to a vertical shear of 130 kilonewtons. And what we're asked to do is plot the shear stress distribution over the cross section. One thing that we know is that it's somewhat parabolic if it were just a solid rectangle. With it being wider here, that's going to reduce the transverse shear stress component, so that's going to drop off. But the other thing we'll notice is that it's going to be symmetric about that neutral axis. So we only have to really solve the distribution for through the center of that, and then just see that it's symmetric. And then we can solve what is the shear force carried by that top half of the plus sign, AB. And those are the 2 specific things that were asked for in that analysis, but I carried this a step further to calculate what the shear force is carried by the center portion. And so the geometry of this plus sign is that each leg is 150 millimeter long, and then each width is 50 millimeters. So that is consistent. And we need to do the analysis VQ over IT. And so we need I to really calculate that for this throughout. I is going to be a constant essentially once we have that for the cross section. And the way I did that was the 1/12 times the base 50 millimeters times the height 350 millimeters cubed, plus then the horizontal section. We've already taken into account this vertical portion, so it's just 1/12. The base would then be 300 millimeters, and the height 50 millimeters cubed will give us 1.8177 times 10 to the 8th millimeters to the 4th. And so main thing is just make sure not to account for this central area twice. And so we did not include that portion in the base here. We did 300, not 350. Based on our discussion of the relationship of the shear stress, we know that the shear stress at B is equal to 0. It's on a top surface. And so really all we need to know is then the shear stress at the critical points at A and at C, and we will know then what the distribution of stress is. A is a little interesting in that there's a shear stress in that vertical portion just above that point A that is a given value, and then just below that point, minuscule amount is the shear stress in the horizontal portion. So we really need to calculate that shear stress at A just slightly above that point and then slightly below that point. But you can just enter in that value in that process. And so we'll go through and do that. And so Q of A then, looking at that shaded portion on the top, is Y bar prime A prime. And so that distance to the neutral axis, the distance to the centroid of this top portion, half of 150 is 75 plus half of 50, 25 will give us 100 millimeters from the neutral axis up to the centroid of that top section. And so that's our Y bar prime 100 millimeters, and then that area is 50 millimeters by 150 millimeters. And so Q for this top section then is 750,000 millimeters cubed. And what we're finding is that we really don't need to solve this as a function of Y. We just need to know the critical points. So that's a little bit easier to do. And so the shear stress at A for section AB is just VQ over IT, 130,000 newtons, Q 750,000 millimeters cubed, I 1.8177 times 10 to the 8th millimeters to the 4th. And that thickness on this top section side is 50 millimeters. And so that shear stress for AB then is 10.7 megapascals. And then we want to calculate that shear stress at A again for that section AC. And if we're going a minute distance down from there, our area is not going to change any if we're talking about infinitesimally small distances. And so our Q value remains the same. The only thing that changes is that T value, that width of that horizontal section. And so that V is the same, 130,000 newtons. Q is the same, 750,000 millimeters cubed. I is the same. Only thing that changes now is the thickness there is 350 millimeters for that section. And so that ends up being 1.53 megapascals for that horizontal section, and that shear stress is distributed over a much wider width. And so we have those two locations now. We have the shear stress at B and the shear stress at A for the vertical and the horizontal section. And now we just need the shear stress at C, and we can fully define the stress distribution. And so now we get to see solving Q for multiple rectangular sections. QC is going to be the sum of Q1 plus Q2. Q1 we already solved as 750,000 millimeter cubed. So now all we're doing is solving for section 2 here. And the total height here is 50 millimeters. So the height of the shaded portion is 25 millimeters. And so the Y bar prime is half of that 25 or 12.5 millimeters. And then the area is 25 millimeters times 350. So that'll give us a QC of 859,375 millimeters cubed. And so V is given. We have our new Q value for location C. I stays the same, and the thickness or width at that point is 350 millimeters. So we have 1.76 megapascals. And so we can plot that, what that shear stress distribution looks like for that section. And for that top half, it goes up to 10.7 megapascals where it meets that horizontal point, and then it drops off to 1.53 as it goes through that wider section, and then it expands back again in a second order fashion up to 1.76 megapascals, and then it's just symmetric. And so if you were to look at A1 and A2 just above and just below that point A there, just above it would be 10.7 megapascals, and just below would be 1.53 megapascals. That analysis does neglect the stress concentrations that would occur anytime you have discontinuity in stress at a point like that. You'll end up with stress concentrations occurring. And so this gives you a ballpark estimate of the state of shear stress at those points without taking into account those stress concentrations. And so that is the answer to part 1, plot the shear stress distribution over the cross section. And the next step now is to calculate the shear force carried by that top portion AB. And so this is where we can use that relationship we just saw for the rectangular section before the break here today. And we can define QAB as the 1/2 h squared over 4 minus y squared times b. This was the same relationship we found for a rectangular cross section. This is valid only for that values between 25 millimeters up to 175 millimeters. Because remember again, when we're solving for Q, it's the area above your point of interest. And so that's still just a rectangle going up. So as we go down, we're still dealing with a rectangle going up. And so that derivation is completely the same for that top portion. The only thing that makes it different than a rectangular section is then the I value. The I value takes into account the entire plus sign in that determination. And so QAB for this top portion, 1/2 h squared over 4 minus y squared times b, that's what we derived previously. And we can plug in our values, height of 350 millimeters squared, and b base of 50 millimeters, and then solve that as a function of y squared. And so that'll give us the shear stress AB. Again, the shear force, Q is a function of y, I we solved, and the width 50 millimeters. And again, we can simplify that down to 10.951 minus 3.576 times 10 to the minus 4th y squared megapascals. And so it's going to vary by placing 25 millimeters in there at point A, then to point B at 175 millimeters. And if you do put 175 millimeters in for y, this term tau AB will be equal to 0. Remember again, it's 0 at the top. So that's a good check to verify that that in fact equals to 0. But in terms of figuring out the amount of force carried by that top section AB, you have to remember back to, I believe it's chapter 1-2 type content, where your shear stress is just defined as then the integral of the shear force AB is equal to the integral of your shear stress AB times dA. And we have our shear stress as a function of y and integrate with respect to area. We have dx dy. We can integrate from 0 to 50, from 25 to 175. And when we integrate the first term, there's no x value, so it just gets an x in there. Plug in the limits of integration. Now we'll integrate again. You end up with a y in the first term, a y cubed over 3 in the second term. Limits of integration. Remember to subtract off the lower limit. And you'll find that your shear force carried by section AB is 50.3 kilonewtons. With that, we're symmetric for the cross section. So we know that the bottom half also carries 50.3 kilonewtons. We also know that a full 130 kilonewtons is applied. And so to calculate out the middle portion, we don't have to do any more of this nonsense. We can just use equilibrium. And the shear of the middle portion is 130 kilonewtons minus 2 times the shear of AB, taking into account the bottom half, which will give you a shear of the middle section of 29.4 kilonewtons. And so always keep track of equilibrium too. If you're trying to solve an additional thing that wasn't asked, you might be able to do that with algebra instead of going the long way through with calculus to solve for that. Let's see, do you have any questions over that, Jordan? And then I think everything that we do in regard to this should be pretty basic polynomial relationships. So integrating stuff like that should not be bad.
Yeah, that didn't look too bad compared to the stuff we had to integrate in ME216.
Okay, yep.
Dr. Rockey's really like to give you some nasty load predictions to integrate.
Yeah, and I think that does help with understanding that variation with respect to position for your stresses and things like that. But for what we're doing here, we're typically going to be dealing with basic polynomial relations. I figure that's nice. Then you don't get mixed up with the calculus of the problem. You can focus on the fundamentals here with solid mechanics. And then if you need to do the more complex type of integrations, you can use software like MathCAD or MATLAB and let it crank through those tougher integrals. And so now we're kind of wrapping things up here with this whole shear formula. Shear stress is equal to VQ over IT, and the limitations that we have associated with this. The first limitation is this does assume that the shear stress is a constant across the width, and that's not entirely true. It's maximum at the edges and kind of dips in the center of that. But when you're dealing with a beam that has a height much greater than the base, so base over height is 0.5, height is twice as tall as the base is wide, there's only about a 3% error between the tau that you calculate with the shear formula versus the maximum shear stress that you find. But as your beam becomes wider and less tall, so your base is twice the height, your error climbs to about 40%. And so that's good to just be aware of that, the limitations of the shear formula when you're dealing with a wide beam, that you're going to have a fairly significant error in that. For a wide flange beam, the error is considerable. You have your flanges on the top and bottom. You have your web connecting the two. You're going to have your max shear stress occurring at the center of the web. No, let me see something here. Oh yeah, we're going to talk about this on the next page, how to get an approximation of that. We mentioned that previously on the last problem, that there's a stress concentration where there's a discontinuity in width. So that point A on the problem we just solved. In that scenario, I guess if we look at that scenario, this is where the stress concentration occurs. So that is kind of bad for that upper portion, because that would increase the 10.7 megapascals where we have a maximum shear stress located. But normally, if it's not in a location of max shear, it would not be a concern. And so just kind of make a note of where that could cause an issue. But in terms of this, this is talking more about the B over H value much less than 1 for the upper portion of that. So there wouldn't be that large of an error just due to the non-constant nature of the shear stress, but there would be a potential stress concentration there. Then next, for non-vertical edges, the shear formula also does not give accurate results either. It kind of flows down in line with the geometry. And so a theory of elasticity is kind of a better approach to get that. But you could approximate this as an average width and get a ballpark number so that you can make comparisons of that with the theory of elasticity. And again, these aren't really common geometries at that point. And then finally, for the I-beam, again, the majority of the shear stress is carried by the web. Remember, the shear stress is 0 at the top and the bottom where the flanges are located. So it's going to increase a little bit through the flange, but then as you get more towards the neutral axis, the web is going to carry that. And so what this actually does is it causes a large Q at the top and more of an average shear stress through the web. And so a ballpark estimate that can be used is just looking at the average shear stress as saying that the web carries that entire shear force divided by the area of the web portion. And so one thing to note about that as you're going through the textbook is this is done correctly in example 7.3. And at C, they go through and calculate the average shear stress to be 26.7 megapascals. And if you do the calculations with VQ over IT for that cross section, taking into account the flanges as well, you end up with 25.2 megapascals. And so you do get into that same proximity if you're just using the average analysis. But then they do this incorrectly in example 11.1 later on in the textbook, where they use the full height or the full depth of the beam for the area of the web. And so my comment on that is, remember, your average shear stress is your shear force divided by the area of the web. And so if you're taking into account a larger area, that's going to drive down your estimate on your shear stress. And anytime we're doing like a ballpark estimate, we want to make sure to use the smaller area, as that would give us a larger shear stress for our estimate. And so you always want that larger estimate of stress, so you're confident in the safety factor that you're getting out of that. If you are concerned about that, like you're overestimating the state of stress, like what we see here a little bit, you can always use the VQ over IT formula for that, or you can use a finite element analysis to get a better understanding of, say, the stress concentrations and things of that nature. But overall, that's what I always recommend as you're going through and doing an analysis. Try to do the analysis so it's a potential worst case scenario, so that you have kind of a built-in factor of safety based on the level of analysis that you're doing. And then in other scenarios, you can often then rely on design codes and standards when the shear becomes significant. But for all of this, what we'll find is that the bending stress is typically much higher and is the critical stress that causes failure. Oftentimes our shear force is constant for a section, changes, drops, constant for a section, whereas bending is going to be a function of X, so it gets magnified in that regard based on the length of the beam. And so what we'll find typically is that the bending stress dominates and is the stress component that causes failure in beams. Transverse shear really becomes important when you have a short, stubby beam. as that bending stress really doesn't have a chance to develop, and it's primarily a transverse shear situation. And so we'll see that as we continue on, as we get into chapter 12. We don't even take into account the shear force contribution to the displacement. We just look at purely the bending alone. And then you have to move on to energy methods to look at the contribution of deflection from the shear component. Let's see. I think the other thing is we have these two competing types of stresses that are being developed. So we have our bending stress and our transverse shear stress. When you get into chapter 11, it's really the same content. It's more focused on the design of beams based on designing to a bending stress criteria and a shear stress criteria. And for those types of problems, what you do is assume that failure is dictated by bending. And so you essentially design the beam based on the bending requirement. And then with that, you can then go back and look, is your shear stress criteria, is that also satisfied? And that's generally, again, going to be the case, as bending is the dominating factor there. And so our next homework that we get into, we'll have problems from chapter 6, 7, and chapter 11, dealing with both just the bending stress and the transverse shear stress, and then designing a beam to meet each of the criteria. Usually the transverse shear is going to be more than satisfied. And that does not take into account displacements at this point. And so as we continue on into the week, on Friday, we'll be discussing the transverse shear stress in built-up beams. When you fasten things together with fasteners or nails, those fasteners would have to carry that transverse shear load. And so you want to make sure to identify the spacing of the fastener so that it can adequately support that transverse shear. And that'll finish us out for chapter 7 on Friday. And then we're getting close to the first exam over our review, axial loading and torsion, as well as the homework related to this. And so by Friday, I'll get the information on the exam together and the homework, and I'll try to stagger those at least a little bit so that you have enough time to do your exam. But my guess is your exam should take about an hour to do. And so if I have one thing due on a Saturday and another one due a few days after that, that should provide enough time. So we'll kind of get your homework evaluated and make sure that's available before your exam one is due, and that we have some time to answer any questions that you have over those first two homework sets, the one that you handed in last Saturday and the one that you're handing in this Saturday. So we'll take that into account, and with the deadline on that first exam. Oh shoot, I was just here looking at the top half. If you ever saw the Tim the Tool Man Taylor show, his neighbor always kind of looked like that, staring over the fence.
Yeah. Yeah.
I wasn't paying attention. I was just talking along and had minimized that so our pictures weren't in the way. Are there any other questions that you have?
So on the exam, when you said, I think I talked to you about this before class started this summer. So the day you put out the exam, how long will we have to do it from the day that you put it out?
It'll probably be in that range of 3 days to a week time frame is
Okay.
what I've initially been giving. And mainly that's so that each one of you can kind of work that into your schedule. If you're working on co-op or elsewhere, it can be difficult to carve out a chunk of time. So if I give you a few days to do that, or up to a week, you can kind of schedule that in accordingly.
Okay, so like I wouldn't have to just like block out like, you know, an hour and a half of time or whatever to do it all at once. I could work on it for a little bit and then put it up if I need to.
Exactly. Yeah. I was going to try that last year where we could find a common time where we could just do the exam over Zoom, where I could watch everyone. But it was just too difficult, even with 20 people, to find a common time for everybody to meet, or even 2 common times. I think we had to go to something like 4 different times. And at that point, I was just like, we'll just do it on your honor system, and you can do this over a few days and submit it through D2L.
Okay.
Other questions?
None right now. I'm sure I'll might have some questions when I dig into the homework.
All right. Well, sounds good. Thanks for joining in today, Jordan, and we'll see you on Friday.
See you on Friday.